Imagine standing on a runway. On your left, a modern fighter jet. On your right, a massive orbital rocket. But flip the switch, and the difference becomes violent. The jet engine wakes up with a high-pitched whine.
A sound that vibrates in your teeth. It is a controlled, rhythmic process. The rocket does not scream.
It crackles. It roars with a low frequency that hits you in the chest like a physical punch. When it lights, the air itself seems to tear apart. One is a masterpiece of efficiency, designed to cruise for hours. The other is a monster of brute force, designed to leave the atmosphere in minutes or die trying. This is the ultimate duel of propulsion. A battle between two philosophies of physics. In one corner, the air-breathing turbofan, king of the atmosphere. In the other, the chemical rocket, emperor of the void. To understand why we cannot just fly a jet to the moon or strap rocket engines to commercial airliners, we have to look inside. Inside the combustion chambers, where physics is trying to destroy the machine from the inside out. Let us begin with the jet engine. Philosophy here is theft. A jet engine is a machine that steals from its environment. It relies on the Brayton cycle, a four-step dance of thermodynamic violence, often remembered by the rhyme suck, squeeze, bang, blow. But these words do not do justice to the nightmare of forces inside. Consider the intake. The giant fan at the front of a modern airliner engine is not just a propeller. It is a precision instrument, spinning at the tips of those fan blades are moving faster than the speed of sound. They are slicing through the air, swallowing over a ton of atmosphere every second. But the air does not want to be compressed. It resists. This is where the compressor enters the fight. Behind the fan lies a series of smaller blades, rows upon rows of them, progressively getting smaller. They squeeze it into a space so tight that the pressure spikes to 40 times that of the outside air. As you squeeze a gas, it fights back with heat. By the time the air reaches the combustion chamber, it is already hot. And we haven't even lit the fire yet. This is where the jet engine plays a dangerous game. It injects jet. A spark ignites it. The result is a continuous, controlled explosion. The temperature skyrockets to 1,700 degrees Celsius. This creates a critical problem.
This temperature is higher than the melting point of the metal used to build the engine.
But engineers found a way. They developed advanced cooling systems, microchannels of air that create a protective thermal barrier. This delicate balance allows the jet engine to harness incredible power without self-destructing. A triumph of engineering indeed.
Think about that. The engine is operating at a temperature that should turn its own internal components into a liquid puddle.
Physics says the structure must fail. Therefore, engineers had to cheat. They developed single crystal superalloys, metals grown as a single grain structure to resist deformation. But even that was not enough. They drilled microscopic holes into the turbine blades. They bleed cool air from the compressor and force it through these holes, creating a thin film of cool air that hugs the surface of the blade. The metal never actually touches the fire. It survives inside a cocoon of air, millimeters away from destruction.
This expanding gas blasts out the back, spinning the turbine which drives the fan at the front and pushing the aircraft forward.
It is a beautiful, self-sustaining cycle. But it has a fatal flaw.
It is addicted to oxygen. The higher you climb, the thinner the air becomes.
At 30,000 feet, the engine is happy. At 6,000 feet, it is struggling to breathe. By 100,000 feet, the jet engine is useless. It is a fish on dry land.
There is no air to suck, no air to squeeze. The fire goes out. The machine dies.
The rocket engine looks at the atmosphere with contempt. It does not need to steal oxygen from the air because it brings its own. Inside a rocket, we are not dealing with airflow. We are dealing with fluid dynamics at the edge of insanity.
Take the Saturn V, the rocket that took humans to the moon. Its first stage had 5 F1 engines.
These were not engines in the traditional sense. They were open vents to hell.
To feed a rocket, you need two things: fuel and an oxidizer. Usually, this is liquid hydrogen or kerosene mixed with liquid oxygen.
But you cannot just pour them into the chamber. The pressure inside the combustion chamber is immense.
If you just opened the valves, the fire would push back up into the fuel tanks and blow the entire vehicle apart.
This requires a turbopump. The turbopump on a rocket engine is one of the most powerful machines ever built by human hands.
It is a heart that church beer eats it and fits in an Olympic swimming pool in less than a minute. It spins so fast that if a piece of sand got inside, the friction would cause it to detonate instantly.
Before the liquid hydrogen enters the chamber to be burned, it is pumped through channels inside the walls of the nozzle. It absorbs the heat, keeping the nozzle from melting, and preheats the fuel for better combustion. It is regenerative cooling. The rocket is cooling itself with its own ammunition. The exhaust gas accelerates through the throat of the nozzle. This is the narrowest point.
The gas reaches the speed of sound. As the nozzle widens into the bell shape, the gas expands and accelerates even further, reaching hypersonic speeds. Newton's third law takes over. For every action, there is an equal and opposite reaction. The gas goes down. The rocket goes up. So, who wins the duel? If the metric is efficiency, the jet engine wins by a landslide. We measure efficiency in rocketry using something called specific impulse. It is measured in seconds. It essentially asks, if you have 1 pound of fuel, for how many seconds can you generate 1 pound of thrust? A really good rocket engine, like the one on the space shuttle, has a specific impulse of about 450 seconds. A modern jet engine on a passenger plane has a specific impulse of 6,000 seconds. The jet is over 10 times more efficient.
Why? Because it does not have to carry its own oxygen. Oxygen is heavy.
In a rocket, 80% of the weight at liftoff is just propellant. The rocket is a truck carrying its own gas station.
The jet is a glider that sips from the air around it. However, if the metric is raw power and speed, the rocket crushes the jet. The jet engine hits a wall called air resistance. As a jet approaches Mach 3, 3 times the speed of sound, the air gets so hot from compression that adding fuel does not give you much more energy. You hit a thermal limit.
The rocket has no such limit. In the vacuum of space, there is no air resistance. There is no drag. To get to orbit, you need to travel at 17,500 miles per hour. That is Mach 25. The heat generated by air friction at that velocity would turn the aircraft into a meteor. But the rocket climbs above the atmosphere.
But there is a twist in this story. The binary choice between jet and rocket is becoming a spectrum. We are seeing the rise of the hybrid.
Imagine an engine that acts like a jet at low altitude, breathing air to save fuel, and then transforms into a scramjet, supersonic combustion ramjet, dips into the chaotic realm of high-speed fluid dynamics.
The SABRE engine takes it further. It uses a precooler,
A heat exchanger that can cool incoming air from one. This prevents the engine from melting and allows it to breathe air up to Mach 5 before switching to rocket mode to reach orbit. Why does this matter? Because right now, getting to space is expensive. It involves building a massive tower. If we can use air-breathing engines to get halfway there, we strip away the weight of the liquid oxygen. We make space travel more like aviation.
We turn a launch into a takeoff.
But until that future arrives, we are left with our two champions. The jet engine remains the marvel of our daily lives.
It shrinks the planet. It makes flight mundane, safe, and reliable. It conquers the horizontal plane.
It connects continents by battling the friction of the air and winning. It is the steady heartbeat of globalization. The rocket remains the chaotic hero of the vertical plane. It is dangerous, inefficient, and violent. It rides the knife edge of catastrophe every single time it lights up.
But it is the only machine capable of breaking the chains of gravity. It is the only voice we have that can speak to the stars.
The jet engine gave us the world. The rocket gave us the universe.
As we look at the future of aerospace, the lines will blur. We will see engines that adapt, morph, and change their nature as they climb.
But the fundamental physics will remain the villain. Gravity will always try to pull us down. Air resistance will always try to slow us down.
Heat will always try to melt our wings.
The engineer's job is to stand between these forces and the fragile payload, us.
Whether it is the spinning blades of a turbofan or the roaring bell of a rocket nozzle, the goal is the same. The duel isn't really between the jet and the rocket. They are teammates in a relay race. The jet takes the baton as far as the...
They are the twin pillars of our ascension.
To keep deconstructing the world's most complex systems and to understand the machinery that drives our civilization,